start this. All right. So I did a kind of a weird thing, I guess. I moved some things around. This isn't so weird. I decided it might be better to just have these kind of empty notes in one spot, and then I'll just keep putting them there. Otherwise, they'll be all over the place. And so I'll keep putting stuff there. And then what happened, because I do want to try to keep the sections kind of separate from each other in the notes. And so I've got September 17th, an assignment for 1.2, September 17th again. And so we're going to keep talking about 1.3. I posted the assignment just so you could have a look at it if you wanted to, but we only just introduced the concept. You could do some of those questions already, but you don't have to. I think I made the due date next Thursday. Let's see. Yeah, on Thursday. Okay, good. So there was my Moodle change up a little bit. For review, we'll just talk about the one page of notes that we did last day, and then we'll pick up from there. So we were talking about rates of change. Oh, that's what it was. This nagging thing. There's something I was going to say. There's going to be a fire drill at 9:45 today, so we'll just kind of end slightly before that, and then not be part of that nonsense. Sorry, I guess that's in the recording. Anyways, just pretend I didn't say that. But just because I have to get to my other class, and anyways, so now you know. Don't be thrown off. But also remind me if I'm cutting it close. You said we were gonna go. All right. So we were talking about rate of change. Rate of change is really no news to us. We don't really call it the rate of change. We might call it the slope, right? And so the rate of change, we can look at something like this and just kind of intuitively say, and maybe I should use a different color for the one that I want to talk about, right? But we can say, okay, here I've got a slow rate of change, and here I have a fast rate of change, right? And what we're talking about is the slope in this case. And we developed it's not so much a formula, it is technically, but rise over run, right? We kind of got there by looking at, okay, I have some input, I have two separate inputs yielding their own outputs. So the average rate of change is going to be the change in the y's, which you can think of as the rise, and the change in the x's, which is going to be the run. So how quickly do the y's change as the x's change? We were given a function as a table, right? And we calculated the average rate of change for both of those, right? We're just taking the inputs, y2 minus y1 divided by x2 minus x1. Which you choose as 0.1 and 0.2 doesn't matter, right? The negatives would cancel, but I usually use the first input as the first point and the second input as the second point. Seems reasonable to me, but it doesn't matter as long as you're consistent. And then I left you with this little guy, so a function as a graph, okay? And I said you can do it, right? You can read a graph. And so let's have a look here, and let's start with A. Now, let's see, how much room did I give myself? Not very much. But what I will do is I'll just do a separate graph for each part. How about? And kind of make them smaller or something like that. There we go. So on the interval from 0 to 1, remember the square brackets mean inclusive of 0 and 1. In this case, it actually doesn't matter. But 0 and 1, so here my x1 is 0 and my x2 is 1. My, I guess I should use the same color. y1 is the output at x1, which is also 0. And y2 is also 1. And we know this, this character as x squared. So we have the average rate of change. And I wish there was a shorthand we could use, but I'll just do it like this to keep it kind of nice and tight. y2 minus y1 divided by x2 minus x1. Like I said, as long as you're consistent about which point you're calling 1 and 2, it doesn't actually matter. You can play around with it. But y2 we said was 1, y1 we said was 0, x2 is 1, and x1 is 0. 1 minus 0 over 1 minus 0, I'm going to go with 1. So the average rate of change is 1. Which means that we don't have to have just straight lines. We can work with curved functions and we can still talk about the average rate of change. But we're used to seeing slope on a straight line to begin with. About on the interval 1, 2. Let's see here. I wonder what the best way to arrange these is. Maybe like that. I can, but it's such an itty bitty. I guess I'm cheap with my virtual paper. That's cheap. The interval, I'll just say from 1 to 2, inclusive, same thing. Average rate of change is y2 minus y1 over x2 minus x1. I want you to get in the habit, or if you're not already in the habit of just writing out the empty formula that you're about to use, just always. It's annoying, but if you tell me that this is what you're going to do, and then for some reason, you know, you misread the values, that's not what we're here for, right? Can you plug in the right values? You knew to do the right thing, and then you just kind of mix up your numbers or whatever. I'm not as concerned about that. What I want to see is, do you know that this is what you want to do, right? And so that's why you should always write out your empty formula first. Okay. Y2 is 4. Y1 is 1. X2 was 2. And Y2 was, or sorry, X1 was 1. Ugh. 4 minus 1, 3 over 1. Yeah. Here. I kind of went a little harder. Okay. So that makes 3/1, which I'm just gonna go straight to 3. Keep it nice and tight. Which means that, okay, we already established between 0 and 1, the rate of change was just 1, right? Kind of a reasonable rate of change. But then as we can see here, between 1 and 2, right, same space of x that we're moving in, but now we're kind of shooting up, right? And so that's reflected in the 3. We've got a faster rate of change in that space. So then what do we want to do? What about overall from 0 to 2? The average rate of change at 0 and 2, y2 minus y1 over x2 minus x1. I feel like my iPad is lagging a little bit, and I don't like that. Hot take, right? Y2 is 4, y1 was 0, x2 minus x1, 2 minus 0, 4 divided by 2, I'm gonna go with 2. Okay. So overall between 0 and 2, right? Then kind of smush that rate of change out that we found. 1, 3, 2.
Why do you give us the x coordinates like their coordinates?
So here, the square brackets make it an interval. So if I did have round brackets, then that would be confusing, because then it would be an xy coordinate typically. But I think, so it does say on each interval. So then it would be clear even with the round brackets, yeah.
What do you mean by interval?
So an interval is an interval from 0 to 1, an interval from 0 to 2. So it's an interval on x. So the x axis. And we talked about intervals last day, where we said, okay, if we have round brackets, then it's exclusive of those endpoints. But if we have square brackets, then we include those endpoints, right? And that's really all we talked about in terms of intervals last day. But it's always for x. I'll make a note here on each interval of x. Good. Any other questions? All right. Now, I'm going to add that page that I am talking about here. What I'm going to do, or what we are going to do, because now, so we've talked about it, we started with a function as a table, then we had the function as a graph, and now we have a function as a function, so as a formula, and we can still find the average rate of change. So we're kind of building up to this. Now, I feel like, well, okay, maybe, because we're just warming up, how about we do A together, and then I want to skip to C and then D together, leaving the biggest mumbo jumbo E for you to try to work through, but I'll add the solutions before I post the notes. Okay. So I've got a little reminder here, right? We said we have been looking at the average rate of change is y2 minus y1 over x2 minus x1. if we talk about the average rate of change for function notation, right, on the interval a, b, then a is going to be x1 and b is x2, or x2 equals b. Oops, that doesn't look very good. Which means that y1 is f of a and y2 is f of b. Remembering that you can rewrite any f of x, f of a, f of b as just a y, right? But now we have this function notation, so it's going to be a little bit easier to look at this and say, okay, I can evaluate f of -1. Right? So -1 to 3. What was my function? X squared minus x. So this means that I was going to keep using this, but what I want to do is actually move to this notation. It's the same, right? But it's going to be a little bit easier to work with later. So here in this case, a is -1 and b is 3. Okay. So to find the average rate of change, we need to find f of a and f of b first. So in this case, right, f of a is -1. So f of -1. So now we're evaluating this function at -1, which means I have -1 squared minus -1. Okay. Negative squared makes it positive. You want to be careful of that, because if you just enter -1 on your calculator and then square it, then it'll give you -1, I'm pretty sure. Let's see here. Because it only squares the 1 and not the -1, so you have to wrap it up in brackets or just drop the negative, right? That's fine too. So just make sure that you're comfortable with that when you're using your calculator. And just remember that it has to be positive. So -1 squared is 1, minus -1 makes a positive, so a +1. Right? 1 plus 1. Bet you didn't think you'd be doing that today. It's usually 2. That's a nice warm-up. How about f of 3? We have 3 squared minus 3. Just showing all my work. If you wanted to skip to 6, that's totally fine. So now I have my input -1 gives an output of 2. So what I could do is I could say x1, y1 is -1, 2. If you wanted to translate it that way, you don't have to. x2, y2 is 3, 6. Uh-oh. Okay. So now, uh-oh. This poor projector doesn't want to do it. I'm going to use the function notation, right, just so we get kind of in the habit of doing that. F of 3 was 6 minus f of -1 was 2. We already showed the work up above, so okay. Shouldn't be so sloppy, Emily. I know. F of 3 minus f of -1 over 3 minus -1. Now I can fill it in. 6 minus 2. Yeah. Divided by 3 minus -1 is 4. 4 over 4. Womp womp. This one. If you want to, you can use Desmos to check it. You have x squared minus x. It looks like this. Oh, why is it not? Okay, that's, whoa. Nothing's behaving today. We had, oh yeah, we were at -1, right? I was looking at 1 and not getting there. But -1 and 3, I don't know why it's looking like that, so let's get out of there. Okay. So the average rate of change is 1 on that interval. Okay. And then I'll add the solution for 1 to 3, right, before I post the notes, but I want you to try it on your own, right? Give it a go. What about the interval of 2 to a? So a is just any value a, right? So it's just going to be a placeholder. Now that's going to be useful later on when we can just put in any value of a and find the average rate of change between 2 and that value, right? So it's going to generate a function of a. So that's cool. But really what we were building up to is, well, this is specific to starting at 2, and same thing, but this is specific to starting at 3 and then moving out h units. Eventually, what we would want to have and develop is some function that we can give it an a and an h and figure out what the average rate of change is for this entire function. And so, and that's kind of heading into calculus, right? So that's the beginning of a derivative, right? And so, which we're not going to do, but it is one of those skills that we need to be able to have, is to be able to find the average rate of change from a to a plus h, so some distance h. But I'll hold your hand for these ones and then leave you to try the mumba jumba. Okay, let's see here. Part C is the interval from 2 to a, remembering that f of x was x squared minus x. What if we just jumped right into the average rate of change with the function notation and evaluated it inside? What does that look like? Average rate of change is f of b minus f of a divided by b minus a. We can make a note to ourselves that a is, uh-oh, this is confusing, isn't it? A is 2 and b is a. Uh-oh. You could change it and then change it back at the very end, but it is good to kind of stretch our brains a little bit like this. And so I'm gonna stick with it where b is equal to a, because a is just a placeholder. But if you wanted to replace this a with b, that's fine. Okay, so then f of b is the same as saying f at a in this case. Right, so here, I'll highlight that. But part of what we need to learn is just to kind of be able to take the function and just evaluate it. Okay? And so then f of a is the same thing as f of 2. And then b minus a is a minus 2. Now the confusing part's over, right? Because now you can just look at these functions and evaluate those, right? You can ignore the a's and the b's. Because now what happens, f of a is, anytime you see an x, you're going to replace it with an a. So a squared minus x. And because I'm doing this twice on one line, I'm going to wrap it up in brackets just to kind of keep them separate, but also because of the subtraction that's happening. And so if there's many brackets, I like to start with square brackets, but you can use round brackets if you want. Isn't that so nice of me? You can use round brackets, but I'm going to use square. A squared minus a minus f of 2, which is 2 squared minus 2. Divided by a minus 2, there's nothing we can do there. That's okay. When I'm simplifying, right, you want to make sure that you can either simplify 2 squared minus 2, or just be careful when you bring in this, this subtraction, right? I'm going to simplify 4 minus 2 to be 2, and then I'm left with a squared minus a minus 2 over a minus 2. I'm going to leave it there. We could factor this, but I think we're okay to leave it here for now, because even though we could simplify it, I think, right, can I pull out an a minus 2 out of here? I think I can, right? I can. A minus 2, a minus, or plus 1 has to add to negative 1 and multiply to negative 2. I'm good with this if you just leave this as your answer. What's that going to do? This gives us the general formula for the average rate of change between 2 and any value a. So then what you can do is you can just plug in your value of A once you have it, and then you can easily or relatively easily calculate the average rate of change between 2 and A. Okay? And I know what you're thinking, why would I possibly want to do that? Why would I care about the average rate of change? The average rate of change tells us about characteristics of the function, right? And so we'll be able to determine if things are, well, increasing, decreasing, that's nice. Concave up, concave down, right? So we'll be able to talk about kind of the shape of the function, which just helps us get to know this function a little bit better. Let's try the interval from 3 to 3 plus h. Remembering that f of x is still x squared minus x. It's this behavior of x squared minus x. I'm going to write it out, but I encourage you to try it on your own, and then we'll kind of check back in once I've written it out. How about that? A big old womp womp. That's nice though. Yeah, so there's a lot of kind of places where things can happen, right? But I will tell you this, the H in the denominator, so the H in the bottom, will always cancel out. So if you're not able to cancel it, then something's gone wrong, okay? And so I'll make a note of that. The H in the denominator will always cancel. Not the H in the numerator, right? But what I was working towards that entire time was just kind of simplifying until I can cancel the H in the denominator. Now let's make another note here. A fraction, just in terms of terminology, because I don't remember saying it yet, but I've already used the term numerator and denominator. And so probably good to have a little refresher on the numerators on the top, because it's numero uno. And then the other one's the denominator. Just have to remember one to remember the other, right? And so the numerator, numero uno on top, denominator. Right? Because I do need you to be kind of fluent with that terminology, okay? So that I can say things like the H in the denominator will always cancel. Okay? So what were some key things here, right? Being careful when you bring this negative inside. Now I simplified 3 squared minus 3 beforehand, and then I just subtracted it. That's fine. Making sure that you treat 3 plus H as one thing, right? So I tend to wrap it up in brackets and just kind of call it one thing. And then, because I wasn't able to cancel the H's quite yet, right? I need to pull out a common H from all the terms in order to be able to cancel it. And so then I kept going and I expanded the 3 plus H squared, which is 3 plus H times 3 plus H, right? Remember that? You don't just want to bring in the square because it's quite different. What else? I did some rearranging. Usually I like to have my variables in descending powers, right? So that's why I moved my H in front of the -9, because then it's descending, but that's doesn't matter. I expanded, and then you can cancel, right? You get a 9, but you have a -9, 6H minus H. So I'm collecting like terms here to get 6H minus H is 5H. And then I can pull out this common H from H squared and 5H, leaving H plus 5. And then I'm able to cancel that H. What does this give us? This gives us the average rate of change for any 3 to 3 plus H interval, right? So moving out H units from 3, I can just plug in whatever H is, and then it'll just give me the average rate of change. Okay. say we can use this to find the average rate of change. It's still pretty specific, but rate of change on 3 to 3 plus h of f of x equals x squared minus x for any value h. On the interval 3 to 4, h would be 1. So then the average rate of change would be 1 plus 5. For example, from 3 to 4, right, means that h, it must be 1. So the average rate of change is h plus 5, 1 plus 5, 6. So pretty quick. Like I said, can try those other ones. I'll sneak them in before I post the notes. So if I tell you that a function is increasing, then you're probably kind of thinking about a positive slope, right, which is an increasing function. And so even though there is this kind of formal definition of what it means to be increasing, we already kind of understand that if I have a function, maybe something that kind of looks like this, would you say that's increasing or decreasing? Just trust your gut. It's increasing, right? And so here, this is increasing. What would something that's decreasing look like? Let's do something like that, right? So if we take it back to this definition, now we have this idea of what increasing, decreasing looks like. So now we'll link it to the function definition, okay? And so a function is increasing if f of b is greater than f of a, okay, for any two input values a, b, as long as b is the bigger value, b is greater than a. Now, might look something like this. We had that condition that b has to be larger than a, okay? So just pick any a, b, and then what you're gonna have is you can map this. This will be f of a. This will be f of b. Now, how we will know if it's increasing, so if a function is increasing on an interval, then the average rate of change is going to be positive, right? And so why is that? And maybe I'll highlight that. Because if you are able to find the average rate of change and you're able to find that it's positive, then you can say that, okay, therefore it's increasing, right? And so, oh, they're gonna work through all the buildings, do fire alarms everywhere. But we know what ours is, not for a while. So the average rate of change is still f of b minus f of a over b minus a. Now, f of b is larger than f of a, right? Because we know it has this shape. And so that would yield a positive number. And then b minus a, b is larger than a, and so b minus a would also yield a positive number. And so what we would have is a positive over a positive makes a positive. And maybe that's okay. Okay, fine. I'll just scooch it down one. Is that one? So now you could use this and say, well, my average rate of change on this interval is positive. So now I know that it's increasing, right? Which could be a follow-up question on the test, for example, right? If I ask you to find the average rate of change, you can do that. I expect you to be able to do that. And then I'll ask you, well, on this interval, is it increasing or decreasing, right? Then you would need to be able to link, okay, I have a positive average rate of change, therefore it's increasing, right? Not that big of a stretch, almost intuitive, but still something I want you to be able to do from this section. So it's decreasing on an interval if f of b is less than f of a for any input values a, b on the interval where b is still greater than a, right? So we have that condition. So let's see what that looks like. So again, just kind of picking any value of a and b, right? As long as b is the bigger one, then I can move up here and say, okay, here's f of a, and here's f of b. Oops. This up. So now in this case, the average rate of change maybe I'll just give myself one more line. Is still f of b minus f of a. That's always the case over b minus a. But now what do we have? F of b is less than f of a, so that's going to yield a negative number. Right? And so now I have a negative value, but b is still larger than a, so now I have over a positive denominator. Now, any negative over a positive makes a negative number, right? And so now I will just always have a negative average rate of change. Okay? I was almost about to write this out again. I was like, oh, I need to make space so that I can write out what I just said earlier. But here it is. It's almost like it's from my mind. Given a function, we can determine if it's increasing or decreasing on an interval by first calculating the average rate of change. And then if it's positive, it's increasing, and if it's negative, it's decreasing. And so that's a two-part question that I might ask you. Finding the average rate of change is obviously harder, and then figuring out if it's positive or negative is a little bit easier. Any questions so far? Okay. Can talk about local extrema a point where a function changes from increasing to decreasing is called a local maximum. Okay? If I said, can you draw a local maximum even without knowing what that is, what do you think that would look like? Let's draw something that maybe has a maximum. There's an idea, right? And so here, this is a maximum. We know that. We could even do the minimum at the same time, but we'll start with the maximum. Okay. So what happens? Well, here, if you look at this part leading up to the maximum, then you've got this increasing function. And then at the maximum, it switches to be a decreasing function. Right? So you already know these definitions. It's just we're kind of linking the two. So we call it a local, just because we don't know what the rest of the function looks like. There might be an overall maximum, right, that happens. Maybe the function looks something like this, and you don't know that. So we're just being particular when we say local, right? Because we don't know what the overall function looks like. But I'll remove that one. If we draw a minimum, a local minimum, we might have a function that looks like, let's do something crazy like that. If you had to draw the minimum here, it might be somewhere here. Now, of course, things are happening here, but closer to the minimum, we're going to be decreasing. And then we switch to increasing. Oh, I guess I should do them on the same side. All right. So there's this flow. Okay. We generalize as the local extrema, meaning extremes, extreme values. And we say local because we don't know what the rest of this function looks like. That's just picky. Okay. So that means that if you find the average rate of change, then you can use the average rate of change to determine if it's increasing or decreasing, right? And then you could figure out where the maximum and the minimums are, where it changes from increasing to decreasing and how that works, right? But I would encourage you to just sketch out both of them, right? And say, okay, so here I've got a positive average rate of change, and here I have a negative average rate of change. Again, here I have a negative, and then I go to a positive rate of change. Bypassing the increasing, decreasing. Let's use screen. So we can have a graph, and we can estimate. Now, this is just kind of eyeballing it because we don't have the function, so we can't do any math on it. But we're going to estimate the intervals on which the function is increasing and decreasing, and also any local extrema. So we can start with the extrema. Or maybe I should use a brighter color for the local extrema. Local because clearly this is not the absolute maximum because it keeps going up, 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 up. I went in the wrong direction. Up, 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 up here. All right, so, but it is a local maximum. And I'm intentionally putting it on kind of nice values of X. Not necessarily true, but that's okay. Here we have a local minimum. Yes. Yeah, because it says estimate, we're just gonna do kind of what's easy. I'm not expecting anything crazy. Okay. So I'll use green for increasing and red for decreasing. That's rude. I know. Focusing on this behavior here leading up to the maximum. Well, we could work backwards from the definition of the maximum, right? Or we can just look at the graph because we have it. And so here, I would say that this is increasing. Then this entire way, I have a negative average rate of change, which means it's decreasing. And then I'm on the upswing again, which would mean a positive rate of change, or it's increasing again. We want to estimate the intervals. So there's a little bit more work to do, right? We need to figure out what the intervals are and how to write them. And so here, what we can assume is that these just go to negative infinity and positive infinity. Right? If it's not shown, you can just assume that they keep going. And so what we're going to have is, maybe I'll just snag this number line so we can talk about it a little bit. Because we had a local max, I'll just say the maximum at 3, just looking at it as a number line, and a local min at 8. And then the interval, remember the interval is for x's, so that's why I'm only focusing on this number line. And so here we said, okay, all these values were positive, so increasing. And then between 3 and 8 is decreasing. Now you don't have to draw this number line. I just wanted to use it to show you what you can do. Now, at the maximum and the minimum, it's doing neither. It's neither increasing nor decreasing, because at that point, the slope is 0. And so here I'll make a note. Oops. At the max and min, the function is neither increasing nor decreasing. Because the slope is 0. Which means what? In our interval, we're going to exclude the max and the min points. Right? So up until 3, it's increasing. And so here, it's going to be increasing on the interval, and we're going to just approach it from left to right because that's how intervals work. From negative infinity up until 3, but not including 3. So I'm going to use a round bracket. And do you remember how to link intervals? We use the capital U to link the union, to link intervals, because it's also increasing from 8, but again, not including 8, but up to infinity. And then it's decreasing. Just between 3 and 8. Again, not including those endpoints. So again, you don't need to draw the number line. If you can just go straight to here from the graph, that's cool. That's all you need to do. Right? But I wanted to show you that really what we're looking at is just the intervals of x. Okay. Any questions about any questions? Yeah.
What about a cubic function? Where it goes and then it's 0 right here, the 0 rate of change.
Mm-hmm.
And then it goes to increasing with the basically increasing to 0.
So I feel like you're talking about an inflection point. Where
Probably.
I think so.
So
Which is
an inflection point.
on the next page.
Okay.
We're gonna get there. But first we have to talk about concavity. So these are apparently companies A and B. I don't know where they got that from, but so if we have kind of the rate of change, so here we've got a large rate of change and here we have a smaller rate of change, that's going to be harder to figure out, right? But the shape that's going to be generated is going to be like this, right? And so I think of it as I've got kind of this cup down, right? And so it's concave down. Whereas this other function, right, where we go from a smaller increase to a larger increase, like we saw in that x squared function, right, any parabola behaves that way, then we've got this kind of upward facing cup, meaning it's concave up. So here's where it changes from concave up to concave down, right? And like you said, maybe something like this, right? Where it changes from concave up to concave down. That's called an inflection point. So here it's up and here it's down. So at that change, it's called the inflection point. Okay. I'm just gonna scooch ahead here. Okay, good. So now from this graph, we're gonna estimate the intervals, remember the intervals of x, on which the function is concave up and concave down. Okay? Which also involves roughly finding inflection points. Okay? And so what I do is I just kind of, okay, I imagine concave up. So that's when the cup is facing up, right? And so this part looks, oh, whoops, thought I was in. This part looks like it's facing up, 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 up. And then here at -1, it looks like it's switching to down. Is it down all the way? At some point, probably here, it switches to being concave up, right? And so here, let's use green for concave up, and I'll do red for concave down. And maybe I can have a little bit of a brighter green. More fun that way. Maybe. Okay. So I can find or kind of talk myself into, okay, the cup is facing up, right? And then here it's facing down. But then I'm also going to make note of roughly around here where it looks like it's changing to be up again. And then it's up, up, up. So at these 2 points have an inflection point. So we'll exclude the inflection points from our interval. So otherwise we need to kind of pick and choose which one's which. And there's kind of no concavity happening there. It's where it changes. And so the interval, should we just go for it? It's going to be increasing. I just need one more line. So let me just see here. It's going to be increasing there. We feel ready to just go for it. Remembering that we can assume that these functions just keep going to negative infinity, positive infinity. It's going to take a long time to get there. But it's increasing on the interval from negative infinity to -1. Round bracket. Getting close to -1, but not at -1. And then picking up again, roughly at +1. So x is +1 to positive infinity. So remember the interval is for the x's. Oh, I said increasing, but I'm asleep on the job here. Concave up. It's what we did. It's just, I said the wrong thing. Concave down. These ones, because I'm excluding the inflection point, we're going to use round brackets, and we always use round brackets around infinity because we can't get there. So round brackets. I wouldn't be too upset if you used square brackets around -1. The problem becomes then if we're looking at where it's concave down and we say it's between -1 and 1, which it is. But then if I've used square brackets here, then I can't use square brackets here because it can't be both, right? And so then I'm going to exclude -1 and 1 from both intervals just to make it nice and clean. Nice. But if it was including those points, then yeah. Cool. So there. Now we have some characteristics of functions all hinging on the average rate of change, of course, increasing, decreasing, all that fun stuff. I think we're ready to move into the next section, which is function composition or composition of functions. Now, function composition is when we stuff a function inside another function. Okay? And so when the output of one function, so we give the first function its input, evaluate the output, and then we use that output as the input into the next function, then we have a composition of functions. Now we're going to write either f of g of x, and we're going to read that as f of g of x, or we can write f composed with g at x. But usually I just read it as f of g of x, just because that's exactly what it says here. And so here we can use the operator, the composition operator, which is a little O, which you can still read as f. Technically it's f composed with g at x, but I still read it as f of g of x. So here, one thing that's really important is f of g of x, or order matters. So in function composition, order matters. Right, so f of g of x is not necessarily the same as g of f of x. I'm being picky because when could they be the same? Well, if they're the same function, but that's basically the only time, right? And so, right, if I use the output of g of x as my input into f, that's going to be way different than using the output of f of x into g of x. And so we can have, I'll use blue, f composed with g of x is the same thing as f of g of x. F of g of x. Either way. You need to be familiar with the composition operator. Right? I'm going to be floating between the two. Today we'll just kind of focus on this function notation that we're kind of used to seeing. And let's see here. If we let some function capital B of t be the number of bushels of apples produced by t trees. So I can tell it how many trees I have, and it tells me, okay, this is how many bushels of apples you'll get. Okay. then we can let P of B be the profit that can be made off of B bushels of apples. So first I need to tell it, okay, how many trees do I have? Then I'll know how many bushels I'll have, and then I can figure out what my profit is, right? This is a function composition. So which one of these has meaning? The number of bushels of the profit of 10 bushels. That doesn't make sense, right? But the profit from the bushels of 10 trees, that makes sense. Right? And so I'll highlight this one and I'll write out what each of them mean in words. P of 10 is the number of bushels. Cutting my hand on this thing. The number of bushels from the profit of 10 bushels. So that's bad. That doesn't make sense. But P of B of 10 is the profit from the bushels produced by 10 trees. Oops. Produced by trees. That makes sense. I'll go ahead and add this page for our work. Oh, it went. I see. Okay, let me fix this. Oh, which one was I doing? There. I had squiggled out because we'll just do one at a time later, but anyways. Add a page for work, done. Notice I have tables representing my functions. Now, of course, my functions could also be represented by graphs or actual functions, numerical functions, right? But we'll start with the tables and go from there. I've got a table for f of x and a table for g of x, right? So you'll need to keep those straight. So A, we want to evaluate g of f of 7. I'll copy this, put her there. So you always want to start with the inside function. So first evaluate the inside function. F of 7 is 6. Because if I give it 7, it returns 6. So then what I have is I really want to find g of 6. So g of 6 is 10. So it's going to be a two-phase process, but as long as you kind of stay calm, you can work through it. How's that for advice? Just stay calm. How about G of F of 5? That's the same as G of 2. And G of 2 is 3. How about F of G of 2? G of 2. So remember, G of 2 is the first function we're going to find. G of 2 we already found was 3. So that means I'm trying to find F of 3. And F of 3 is 7. We can stuff the same function inside the function. F of 3. You can do that. What happens then? F of 3. I'll bring the table down so we can see it. First, we need to evaluate F of 3. F of 3 is 7. So then F of 7 is 6. Good. We already worked with functions, compositions. Right? Didn't really call them that, but when we had, so for example, when we said B was going to be A plus H, we did 3 plus H, but then I let you do the A plus H on your own, or you will. Then F of B is really just a function composition, right? Because A plus H is a function of A. We have already seen it, but with the A's and the B's here kind of confusing, I'm going to erase it. But just so you know, we didn't call them compositions, but we've already stuffed functions into other functions. And we'll continue to stuff functions into other functions. So again, working through the table, graph, function, kind of types of ways that we can see functions. And so I've just copied the same example 4 times. So then here, we're going to do A, B, C, D. Okay. First thing to note is our function names. We've got K of X and M of X. That's good. These graphs tell us the output for some domain of input. And so for the first thing we want to do here is maybe I'm finding that a little distracting, so I'll remove those. But m of k of 1. First thing I need to do is start inside, right, and evaluate k of 1. Now k of 1 takes an input of 1 into k, and the output is 2. So m of 2. So now I need to move over to the m function and give it an input of 2, and it looks to me an input of 2 yields an output of -1. So as long as you keep track of which function is which there, k and m, right? We're doing the same thing as the table. And sometimes, I mean, if you zoom in really closely and you're really picky, then maybe 2 isn't necessarily -1, but I just want you to pick kind of the most obvious numbers. Let's do, and again, I'll just use the highlight instead. M of k of 2 first thing I need to do is input 2 into k and find the output is 0. So that's going to be m of 0. M at x equals 0 looks like it's at 3. I guess so. Same thing. K of m of 0. Well, I guess it's not really the same thing. It's just the function order is different now. So now we're going to start at m of 0. M of 0, we already said, was 3. So we're going to try to find k of 3. K of 3 is -2. I do want you to try these on your own, but just so I don't forget to add them in, let's do this last one. K of m of -1. M of -1 goes up to 2. So I want to find k of 2. K of 2, we already said, is 0. So now we've used tables, graphs. I think we're ready, bless you, to use an actual function. We've got this f of p is 2p minus p squared, and we want to evaluate f of b, f of 3x plus 1, and then f of the root of p. And so whenever you see a function like this, right, just like we did before, f of x, f of a, we plug in an a wherever we see an x, we're going to do the exact same thing here, right? But each of these inside values could be represented as a function, right? And let's see how much space I gave myself. Not very much. Okay. I'll try to use different colors. F of, I'll start here, f of p, just writing out my general function that I'm gonna stuff things into, because now it should be obvious, okay, f of p, if I wanna find it at b instead, then that's just going to look like 2b minus b squared. And see how much room I need. I guess not. F of, oops, 3x plus 1. Remembering to treat the 3x plus 1 just as one thing going into this original function f of p, should jot it down, is 2p minus p squared. So wherever you see a p, you're going to replace it with 3x plus 1, making sure you keep it all together. So 2 times 3x plus 1 minus 3x plus 1 squared. I'm going to do a cleaner x here. Simplify this a little bit, right? I have 2 times 3x plus 2 times 1. So I can bring that 2 inside and I can get 6x plus 2, and then be really careful about this square. In fact, I'll make it more of a 2. Because what I'm going to do is I'm going to expand this out, right? 3x plus 1 times 3x plus 1. And you might be really good at expanding, but I am not. And I always just write it out. And I have to do the, do you guys call it feeding the chickens? You have to feed the chickens.
Yeah.
So I always have to feed the chickens. I just can't do it in my head. And that's okay. Making sure you keep this negative here, right? In fact, if it helps you, you could throw some more brackets on there just to make sure that you keep that negative outside, but then also bring it in when you're done expanding. Okay, so we get 6x plus 2 minus 3x times 3x makes 9x squared, and then plus 3x plus 3x plus 1. Six x plus 2, and then in the same move, I'm going to simplify the 3x plus 3x to make 6x, but I'm also going to bring in the negative on each of these terms. And so minus 9x squared minus 6x minus 1. Remembering this minus has to get distributed across all of them. Now there's some cancellation I can do here. And in the same move, I'm going to rearrange my powers of x from in decreasing order. It's just a nice way to write out these polynomials, 9x squared. So negative 9x squared, 6x minus 6x. I don't need to worry about that, but 2 minus 1, I can write plus 1. I'll do this, and this is pretty weird. How about that? F of root of p. So now I have f of p is 2p minus p squared. But I want f of root of p. So wherever I see a p, I'm going to replace it with the root of p. 2 times the root of p minus the root of p squared. 2 root p just stays 2 root p. There's nothing I can do. But root p squared is just p. Good. Okay. Let's see here. And you could pull out a root p, but I don't think that it would simplify it that much. So I'm just going to leave it. One thing, so now we can talk about different functions. So I want to evaluate f of g of p and then compare it to g of f of p. And what we'll find is that they're going to be very different from each other, right? And so we have a function g of p is 1 over p, and f of p is root p. Okay? And so what I want to do is, I do want to do that if there's time, but what I want to talk about is the domain of compositions of functions. So remember, we had those rules that we need to have memorized, right? I can't divide by 0, and I also can't take the even root of a negative number, right? And so now what happens is we need to think about, so we have to satisfy the domain of the inside function. Otherwise, I don't have anything to stuff into the next function, right? But then if I'm solving for general values of x that have to satisfy this function composition, right? Then it makes sense that the inside function has to be satisfied and then the outside function. Okay? So there's kind of 2 levels of the domain. Okay? So first, let's talk about the domain of g of p. What's the domain of g of p? P can't be 0, right? As soon as I'm dividing by 0, I'm in trouble, right? So here, p cannot be 0. How about the domain of f of p? I can't take the square root of a negative number, and so p has to be greater than or equal to 0. So we'll just also keep track of the domain as we go. And maybe what I should do is just bump this down. Can I do that? And I'll put this thing that we talked about, the domain, up above so it makes more sense. Hey, good job, Emily. Wow. And then this guy gets bumped down, probably on the next page. Okay, let's do f of g of p. I know. Looked so hopeful. F of g of p means that I need to stuff g of p into f of p. Now g of p takes an input of p and yields an output of 1 over p. So this is the same as f of 1 over p. Yeah. And let's say where p can't be 0. Because that's the domain of g of p. Right? Because G of P needs to yield some output for us to be able to stuff it in. Imagine if the table, so if we go back to the table version, if there was no input to get an output to stuff into the next function, right? That's the same thing as what we're doing here. So f of the 1 over p is the square root of 1 over p. Where 1 over p has to be greater than or equal to 0. Where 1 over p has to be greater than or equal to 0. But we can combine those into one domain if we wanted to. Okay, we'll stop there because we got to pack up before this fire drill. So we'll pick up there, but try these on your own and we'll use them for review, I guess, on Tuesday. All right, crazy.